So hello everybody, in this video we are going to solve a problem from feedback circuit. So this is a voltage series feedback configuration and the problem is an amplifier with the AV equal to 250, ZI is equal to 200 kilo ohms and Z0 is equal to 2 kilo ohms and FL is equal to 5 kilohertz and FH is equal to 50 kilohertz is connected in a voltage series feedback configuration with feedback factor of 0.1. Determine the modified AV, ZI, Z0 and bandwidth. So this is the question. So from this we understood that this is a voltage series feedback configuration. So this is your voltage series feedback configuration and this can also be called as voltage amplifier. So if you understand this configuration, then you better recollect the formulas which are used to solve this problem. Okay. So let me explain this configuration. So this is your input side and this is your output side. This is a two-port network and here the source voltage is Vs and the input to this circuit is Vi. And this is your amplifier, right? So without this feedback connection and all, if it is not present, okay, then this amplifier is an open loop. This is an open loop amplifier. So for this open loop amplifier, the gain is V naught by Vi because at the output side you get the output voltage as V naught and your input voltage is Vi. So we call it as AV, the voltage gain that is equal to output by input. Since it's the ratio of output voltage to input voltage, it's called as voltage amplifier. And then to this open loop amplifier, we are connecting a feedback network. So this is your feedback network. Takes the input from this output voltage. So this V naught is the input to this particular network. Okay. And this is the input side of this feedback network. And this is the output side of this feedback network. So to this feedback network, this V naught is given as the input and Vf, that is feedback voltage, would be the output. Okay. So how the connection is taken? If you look at this, here you take a connection and here you take a connection. Okay. So this type of connection, that is you are taking connection at 2 points from 2 ohms. Then this is called a shunt connection or you can also take it as parallel connection. So you take the parallel connection and then give it as the input to this feedback network and this feedback factor is taken as beta. This is your feedback factor. So this word is mentioned in your problem. Okay. So this is equal to Vf output by input, right? So this is your output. Output is Vf divided by V naught. So this is how we decide. Now coming to this input side. So this Vf will be mixed here. So this side is plus, this side is minus. So at the input side, this minus is being mixed. Okay. So how it is being connected to the one line here. Here only it is being connected, right? This is being mixed. So at the input side, we call this as mixing circuit and at the output side, we call this as a sampling network. Input side, it is the mixer which mixes the feedback input with the source or the external input and at the output side we take the sample. Okay, this is called sampling network. So when you connect it to one arm at the input side, the feedback input is connected to the one of the external input or the source input, then this is a series type of mixing. Okay, so you should know that sampling is taken at the output side and here two arms are involved so that it is a shunt or parallel type. So when you have a shunt or parallel type, then it is nothing but voltage. And at the input side, when you mix it to the input voltage and it is done using single arm, then it is the series connection. So how we are actually naming this, already I told you that it is a voltage amplifier. The other name is the output side thing is taken as voltage, that is mentioned first. Then the input side mixing is taken, so it is series. voltage series feedback amplifier, like that we mentioned. So I hope this would give you the understanding about the naming. Okay. Now coming to this point. So here, when you look into this, you will be getting the ZI, isn't it? And when you are looking into this, it would be Z naught. So once this feedback configuration is involved, actually the Z naught, ZI or the input impedance. This is your input impedance and this is the output impedance. So output impedance of this particular amplifier, that is without feedback. So after involving or after connecting this feedback network, when you are looking into this, this would be ZIF, that is input impedance with feedback. So when you are looking into this after connecting this feedback network, then it becomes Z0F, output impedance with feedback. Similarly, you will be having the changes in the amplification factor, the gain. So that is taken as AVF. Voltage gain, initially it is taken as AV. With feedback, it is taken as AVF. Okay. So these modification we have. So when you look into this, how actually these impedances get affected as well as this gain is getting affected. So I told you already that here you have the series connection, right? Series type of mixing. And here you have the shunt type of sampling. So when you take the shunt type connection, it is the parallel connection I told you. So it will give you some impedance at this side, right? So already you have this impedance earlier. That impedance is Z0. Now because of this feedback network, again some more impedance will be coming, but it is having the effect of shunt. Okay. So shunt means it is parallel, right? So when you have the parallel effect, what would happen actually? The initial impedance will get decreased. Okay. So you have the decreasing effect. Which one decreases? Z0 actually decreases, and now you are getting new one, that is Z0 F. So when you compare these both Z0 and Z0 F, Z0 will be greater actually than this Z0 F. Similarly, when you look into this ZI and ZIF, since we have the series connection, whenever you have the series connection of the resistances or impedances, what would happen? Final effect is increasing. So what is the meaning of it? Here you see, suppose if you have 10 kilo ohm already, that is your initial thing, Z0. Okay, some more 10 kilo ohm is further added. That means it is connected in parallel. So you have parallel connection. So when you calculate this parallel thing, it is 10 into 10 divided by 10 plus 10, right? So it is 100 by 20. So it is equal to, you get it as 5. So the parallel connection will reduce. So it becomes 5 kilo ohm. Because if you have 10 kilo ohm initially, and in series connection you have another 10 kilo ohm. So for series combination, we have to sum them. Okay. So you will be getting 20 kilo ohm. So the total output impedance here getting decreased because of the shunt connection, and here the total input impedance after feedback or with feedback getting increased. So this one increases. Okay. So this is how you should understand from the wording itself, right? Since it is voltage series feedback amplifier, this word voltage indicates it is at the output side, and voltage means it is actually shunt is equivalent to parallel. That means the output impedance effect is decreasing, and at the input side, voltage series means this is corresponding to input side. So this talks about series combination of the things. So series in the sense ZIF actually increases. So how much it is getting increased? That is the thing. Whenever you have this feedback, this factor is important. 1 plus A beta. Okay. This factor is very much important. That plays the role everywhere. So instead of this 1 plus A beta, you can also write it as 1 plus AV beta. There's nothing but this AV or A that is equal to this V naught by VI ratio. This beta is the feedback. Okay. So now I'll give you everything with the help of this factor. So initially, suppose if you have Z naught F, actually what is happening to the Z naught F? It is getting decreased, isn't it? How much? It is by the factor Z naught divided by 1 plus AV beta. Okay. So Z naught F is equal to Z naught divided by 1 plus AV beta. Similarly, you have Zi. Then now after feedback, it changes to ZIF. But it is the series connection. Here it is the shunt connection. And input side it is series. So what happens? It actually increases. How much it is increasing? Zi multiplied by this 1 plus AV beta. Only this factor. 1 plus AV beta. So increases means you should multiply, right? Reducing means you have to divide it. Okay. Then what happens to this AVF? This AVF is also getting reduced. It decreases. Why? Because we have the negative feedback. This is negative feedback. You might be knowing this. I have already told you that on this side, this is plus, this is minus for this feedback voltage. So when it comes here, it is plus and minus. So this minus is getting here, right, to this Vs, so that you are having this negative effect. Okay, so it is a negative feedback. So this Vi actually would be equal to, Vi is equal to this Vs minus Vf, like that it is coming. Okay, so this external source voltage is getting reduced by the amount of this feedback voltage, then it is given as the input voltage. Okay, so this AVF is getting reduced. How much it is getting reduced? By the same factor. So getting reduced means this AV divided by 1 plus this AV beta. Okay, so whenever you have the reduction, just simply divide it by 1 plus AV beta. If you have the increase, then you multiply it by 1 plus AV beta. Okay, so three terms are over. Now coming to this bandwidth. So what is bandwidth? Bandwidth is the frequency range of frequencies. That is higher frequency minus this lower frequency. So we have one more concept, very important concept, that is gain bandwidth product. Okay, so actually this gain bandwidth product will be constant. It is always a constant. This concept you should know. So here I have already told you this gain is getting reduced. If the gain is getting reduced, but we want to maintain a constant value, because of this concept gain bandwidth product is multiplication. Okay, so now whenever you multiply this gain and the bandwidth, it should be a constant. So if it is decreasing, automatically the bandwidth should increase in order to maintain the constant value. Okay, so already I have told you that because of this negative feedback, the total circuit gain getting reduced by a factor of 1 plus AV beta. Okay, that is AV divided by 1 plus AV beta. So if the gain, this is your gain, voltage gain with feedback, isn't it? AVF. So it is getting reduced. Then this bandwidth should get increased, right? So this bandwidth after feedback actually increases. You know how actually this is being calculated from this plot, that is frequency versus gain plot. Suppose this is your frequency and this is your gain or magnitude. Usually it would be appearing like this for any amplifier and all thing is like this. So here this is the maximum gain. This is the maximum gain. This A that is equal to 0 dB. Gain is marked usually in dB, isn't it? This frequency in hertz or kilohertz. So how it is the frequency range or the bandwidth is calculated? Here we are taking this minus 3 dB. So there we mark the two intersection points with the 3 dB, minus 3 dB. So if you draw a vertical line, that indicates your lower cutoff frequency and the higher cutoff frequency. So when you find the range, this would give you the bandwidth usually. This is the bandwidth. FH minus FL is your bandwidth. But I told you that after feedback, what happens? The gain decreases. So in order to compensate for that, the gain bandwidth product, this would increase. So increase in the sense this lower frequency has to shift to the left side and upper frequency has to shift to the right side. So this is with feedback, this with feedback. Okay, FLF. Okay, the gain actually decreases. So gain effect will be getting somewhat decreases like this. You may be having decrease in the gain. For that, the 3 dB frequency would be like this. So this can be your new gain. Okay, this level. It comes to some 0 dB after that. So for that, the minus 3 dB would be coming around here. So you would be getting new FHF and FLF, right? So this would be your calculation for bandwidth after feedback or with feedback. So this thing is actually increases, right? FH, FH increases so that you are getting FHF as FH multiplied by this 1 plus AV beta. And what happens to FL? FL is going to left side, right? So it decreases. So you get a new FLF, but it is decreasing, right? So it is FL divided by that 1 plus AV beta. Okay, now simply you can recollect the formulas directly and substitute them, right? AV is given as 250. You can calculate AVF. You know the concept. AVF is getting reduced as it is a negative feedback. Okay, so it reduces. How much it reduces? It is by the factor of this AV divided by 1 plus AV beta. Okay, so you can calculate it. So it is 250 divided by 1 plus 250 multiplied by what is the feedback factor? Its value is given as 0.1. So that is equal to 250 divided by 1 plus 25. So it is 250 divided by 26. So the answer is 9.615. So you got the first answer. Find the modified AV. Modified AV is nothing but AVF. That is equal to 9.615. So this is the first answer you get. Now we go for ZI. What is the ZI already given? ZI is given as 200 kilo ohm. So we want to find out ZIF. So what would happen to ZIF with feedback? The input impedance with feedback, whether it increases or decreases, it increases. Why? Because we have the series mixing from this word. This indicates your input side. Okay, so if you have the series type of mixing, then that impedance increases. I gave you one example, 10K plus 10K, right? So how it is decided? There you have to put it as, there you have to write it as that Zi multiplied by 1 plus AV beta. So simply, if there is increase means, as per the concept, if it is increasing, then you just multiply by this factor. If it is decreasing, then divide it by this factor 1 plus AV beta. Okay, so what is the Zi value given? It is 200K. So 10 power 3, 200 into 10 power 3 multiplied by, what is the value we got for this 1 plus AV beta? It is 26. Already we have calculated, right? So that is equal to 5200 into 10 power 3. So it is 5200 kilo ohm, or you can also write it as 5.2 mega ohm. So you got the answer now, the second answer. So ZIF is equal to 5.2 mega ohm. So this is your second answer. So we got the second parameter. Then what it is? It is Z naught. So Z naught is output impedance. This is your input impedance, right? So Z naught is output impedance. So what's the value given for that Z naught? It is 2 kilo ohm. So it is 2 kilo ohm. At the output side, we have the shunt connection, right? Voltage indicates it is shunt. shunt shunt sampling. If you have current amplifier, current at the output side, then it is series. Okay, it is voltage. Now we have the voltage series. So voltage indicates it is the shunt connection. That means parallel connection. So parallel connection means Z naught F. That what happens to Z naught F? It actually decreases because here we have the shunt type sampling. So if it decreases means what you need to do is you have to divide the Z naught by the factor 1 plus AV beta. Z naught value is 2 kilo ohm, 2 into 10 power 3 divided by 1 plus AV beta value. Already we know we have calculated it as 26. 1 plus 250 multiplied by zero point 0.1. So that is 26. So this value is equal to 76.923 ohms. It is getting reduced from this 2 kilo ohm, right? It becomes ohm 76 or 77 ohms almost. Okay, Z naught F is equal to 76.9 ohms. So this is another answer we got, the third parameter. The last one is the bandwidth, right? So for bandwidth, we are given this FL as 5 kilo ohm, FH as 50 kilo ohm. So I already told you, FL, it is getting reduced. FLF, it reduces. That means initial, that means FL divided by, if you write it as FL divided by 1 plus AV beta. So FL value is what is given for FL, it is 5 kilohertz. So 5 kilohertz means 10 power 3 divided by 1 plus AV beta is 26. So for this we get the answer as 0.192 kilohertz. So 5 kilohertz is getting reduced to 0.192 kilohertz. Then what happened to FH? Initially FH is 50 kilohertz and this is actually increasing, right? So FH as the effect of increasing, right? That means we have to multiply this FH by this factor 1 plus AV beta. So FH is 50 kilohertz. So 50 into 10 power 3 multiplied by this 26. So we got this as 1300 kilohertz. So now you can find out the range. So it is FHF minus this FLF that gives you this bandwidth after feedback or with feedback. So that is equal to 1300 minus 0.192 kilohertz, right? So this bandwidth with feedback is equal to 1299.8 kilohertz. So shall we summarize the answers now? So the modified AV, ZI, Z0 and bandwidth, right? So AVF is equal to 9.615. Initially the AV is given as 250. So this is your answers at this side. This is the initial data given. This is initial value or initial data. And we got this modified values. Okay. Then ZIF, we got this as 5.2 mega ohms. Initially, this ZI is given in our problem as 200 kilo ohms. Then Z naught F, that we determined it as 76.923, right? This much ohms only. Z naught initially we had it as 2 kilo ohms. So it decreases, right? Decrease. Okay. Then bandwidth with feedback, that we got it as 1299.8. This is kilohertz. And the initial bandwidth we haven't calculated anyhow. We can calculate it as 50 kilohertz minus 5 kilohertz, right? So it is equal to 45. FH minus FH. So it is 45 kilohertz. Now it increased to 1300 approximately, right? So this is the answer we got. Hope you have understood this. Thank you.